Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today's going to be pretty cool because what we're going to do is we're going to look at how a flyback converter works, and we're going to see how it works in this lab power supply, this bench power supply from Nice Power. I've done several videos on this now, looking at different aspects of it. And the last one I did was I used 3 different thermal cameras to kind of show things and power levels and that. I thought that was kind of cool. But in this video, I want to show you the flyback converter that's sitting right here. If you've seen the other videos where I talked about this circuit and how things are laid out and so on, I've kind of highlighted this flyback converter. It's often called a housekeeping power supply because when you have a bench power supply like this where the output, running off this main transformer can have a failure, whatever, and you're trying to control it, current limit it, set the voltage and all that stuff, you want a circuit that's sitting down here looking at your control knobs, putting stuff on the display. You want that all to be able to operate independently. So you put a housekeeping power supply, auxiliary power supply, it's called by different names, but so it'll come off the input power, give you an isolated secondary power to run your op amps and your control circuits, okay? Yeah, so let me zoom into this and I'm going to point out some of the main circuit elements, okay? All right, so what I'm going to do is I'm going to hold this a little bit closer to the camera so you can see a better view of it, okay? So as we talked about before, the power comes in along this bottom rail, comes up. One of the wires goes directly to the board. The other one goes to the power switch to the other side of this capacitor. So it goes through this EMI filter right through here, okay? And then it comes out of this EMI filter and goes back through another, fuse and then another filter. So I'll show you that guy real close. So that's the fuse, that little thing there. And yeah, so it comes back through. There's a bridge rectifier right there, that little black guy right there next to that yellow cap. And then you have your bulk capacitor. It's kind of odd, the placement. Should be on the other side of the CMI filter since the flyback we're talking about is right here. So here, let's get a little closer. So the flyback transformer is right here. The control chip's right up there. And that control chip is basically, it's a control chip with the built-in FET, okay? So it's actually turning on and off at probably around 100 kilohertz. We're going to look at the data sheet and see what that is, okay? And then you have your support elements right around in this area, resistors, capacitors, so on. They help that chip run, okay? So yeah, that's going to switch on and off the transformer. It's going to pull current from this bulk capacitor. So you got this pulsing current going right across your EMI filter. Yeah, that's nowhere near ideal, okay? But anyway, we're going to talk about the flyback. So basically, we're going to ignore this. We got the bulk capacitor feeding this transformer and this guy switching and controlling the output voltage. Now the output, I'm going to just kind of point it out and then I'll show you on the schematic. See these diodes right here? Each one of these diodes is an output. So it turns out, I think what we have is 1, 2, see these aluminum electrolytics, these bulk capacitors? That's an output, that's an output, that's an output, and then these 3 here make up an output. So it looks like we probably have 2 capacitors and then an LC filter for the final output, okay? And that's probably powering up all these, these things here where we want very little noise, okay? And so let's go, and also this other control chip, by the way. So it's probably powering all this stuff, this other control chip that is running the main output, okay? So we're going to go look at the data sheet and then we'll come back and look at this and I'll point out these parts again, and I think it will help you see where these things are. Okay guys, so I'm going to take you to the data sheet I have right here. I'm going to kind of walk you through it, okay? So let's take a look. This part is made by Power Integrations. It's what they call the TinySwitch 3rd generation, okay? And it says there's a family of them. So this is the TNY 274. Yeah, so I think we're actually using the 277. Here, let me come down here and show you this table. So this output power table shows you the different parts you can get. They have different power levels. Now there's two columns on the left that come under 230 volts. In this case, we're going to be 120. On the two columns on the right, that's universal. It goes up to 265. So it actually covers the 120 and the 230. But again, we're going to be at 120, but we still have to look at those columns because the main thing about it is at 85 volts. So at 85 volts, guys, when you have a low voltage input and you're putting out a certain amount of power, you're going to still have to put out that power. So if you have lower voltage, Ohm's law says you have to have higher current, right? So, and that's where this thing called negative impedance or negative resistance in switching power supplies comes from, because the resistance actually drops at the input, you know, when you need more power, okay? So let's go back here and look at this. Now the 277 with an adapter, you get 8 watts. And with an open frame, you get 18 watts. You know, because you're going to have some cooling with an open frame, with the adapters enclosed, right? So it's stagnant air. So that's why you're going to get less power. But 8 watts is going to be plenty to do the kind of things we want to do. Now let's go back up and look at the schematic. What you see is the power at the left side. Hey, look, they're ignoring their bulk capacitor too. So they're just showing plus and minus. That's coming off the bulk capacitor. And then that circuit at the top left, the resistor, capacitor, and diode, those things are your snubber network, okay? And I'll talk about that in a minute. But the main thing you want to look at is that transformer. The transformer is tied to the D, the drain of this chip. So look at that chip right now as a FET. So you have the drain source, and that's going to turn, it's going to pull that drain down to source, and it's going to do it at, we're going to find out, let's say 100 kilohertz, okay? When that gets pulled low, that dot gets pulled down to ground, so the other side, you know, the top side of that transformer on the primary, so this would be the primary side, it's a non-dot. That non-dot's going to be positive, you know, current flow. As conventional current flows from top to bottom, you get a positive to negative, so the dot's negative. So on the secondary side, the isolated side, the dot is going to reverse bias that diode, so no current flow. So that's why this is called a flyback, because it waits until that transistor turns off, which when that happens, you have, let's say, just for, you know, talking point, make it easy, you had 100 volts at the input. So when you turned on, you put 100 volts across that winding, that primary winding. When you turn off, well, you have 100 volts at the input, but now you also have 100 volts you generated across that winding. And so, you know, what's going to happen is that dot is going to become essentially double the voltage. We're going to show you a waveform and show you what it really looks like. There's going to be a spike because of the leakage inductance. You don't have perfect coupling from primary to secondary side. So that's what we call leakage inductance. It's what doesn't help you, and it causes a spike. And so that's why this number on the left side, okay? That diode gets forward biased, it charges up that capacitor, and it helps dissipate that spike. That resistor is in parallel to capacitor to drain the capacitor during the other half of the cycle when the winding's getting charged and that diode's reverse biased, okay? Okay, so yeah, we'll talk about snubbers in another video, and I'll show you how to design those. Okay, now on a flyback, they often call this an inductor because the transformer acts like an inductor. When that when the transistor turned off, then that dot went to like double the voltage. So now it's positive. So on the secondary side, now it's positive. So that the diode connected to that gets forward biased, and that's current flow, and it charges up that bulk capacitor. And then we have this little network over there that's tied to an optocoupler, and that's going to charge up, and that's how you're going to get your voltage feedback and your regulation, and also your isolation. So that optocoupler is galvanic isolation, right? You don't get any DC current flow from secondary side to primary side. Okay, so that's your simplified circuit. Now, product highlights, maybe you've looked at those. There's some enhanced safety and reliability features. There's this EcoSmart stuff where it wants to run on really low power when it's not operating, when it's disabled. So basically, it doesn't look like it's powered. The thing I do want to point out, though, is under product highlights, right down near the bottom, frequency jittering reduces EMI filter costs. So what will happen is the frequency will just dither a little bit. It'll just, change frequency, let's say from 100 kilohertz to 120 kilohertz. That way the energy at the switching frequency is spread around. Okay, that's the idea of that. All right, so let's just go through this. I want to show you a couple things. Here's a block diagram. So there's a lot going on in that little chip. There's the FET on the far right. That's the main part, the drain, source. Those are your two pins. And then up in the top left corner, you have another pin, or the BP/M. That's a multifunction pin, and it does a whole bunch of stuff. One of the main things it does is it supplies power to the chip. You can see the two current sources on the left, and then going across the right, you can see the regulator to the far right. And those other connections go down to power, like the OVP latch in the bottom left corner and all your other circuitry in here, okay? But the fourth pin that you can see is on the left corner, bottom left corner, and that says enable under voltage, okay? So that's your enable pin. So those are your pins you have, and yeah, there's a lot going on. Leading edge blinking, that's where you want to ignore when the FET first turns on because a little spike of current happens, and you want to blink that out so you don't current limit just because you see this, like, a spike that maybe lasts for 100 nanoseconds or less. So there's a lot of things going on there. There's thermal shutdown, OVP latch, auto restart. There's an auto restart so that if you have any of these faults, like right above the auto restart, it says line under voltage. So let's say if you drop below that 85 volts, well, you're going to burn up this FET if the voltage drops too low and you're still trying to put out your power. So you'll have an under voltage lockout wherever you want to set that, okay? And any one of these things that it sees, over current, thermal shutdown, any of those things, you'll have an auto restart. Okay, so there'll be a counter in there, it says, and it'll wait a certain period of time, and then it'll try to restart and see if the fault has cleared. If it hasn't, it'll go back into fault mode and it'll retry. Sometimes that's called a hiccup because it hiccups and tries again. Okay, now look at this chip. The chip on the 4 pins on the right are all S. They're all the source pins, okay? The bottom left one, pin 4, that's the drain. So there's your FET, your drain to source, okay? Then the top 2 pins are up in the top left corner. And we missed pin 3, right? Well, I'm sure it would have been nice to use, pin 1 and 2 are doing multifunction things. It's like, wow, we could have used pin 3 to do something. But what we want to do is we want to have some spacing between our drain voltage. You know how I said that's going to double in voltage? It could go to a high voltage. So you want to have some physical spacing between pin 4 and pin 2, okay? And also from pin 4 to any of the pins on the other side. So that's why pin 4, the drain, the high voltage pin, is stuck in a corner all by himself. All right, so this waveform here, this is the one where you can see the dithering, or how the frequency, you can see down below it says 128K to 136K. So it's going to change frequency, and it's not going to just go from 128K back to 136K back and forth like in a controlled, like, linear fashion like that. Because if it did, it'd end up spending extra time at the two ends, right? So the two ends at 128K and 136K, you'd have a little bit more energy, a little bit higher spike at your EMI. So what it'll do is, well, at least I'm assuming this, but usually when they started doing this stuff way back when, they found out that was a problem because you get this bathtub kind of effect you know, the two edges have more energy than the stuff in between. So it kind of it'll probably bounce around in between those things and try to jump around so the energy spread between those two frequencies. So, you know, you don't get the sharp, well, you do still kind of get sharp edges, but there's other ways to control that. The other thing is, see where the FET turns on over on the left side? Goes down to 0, and then it's on for, you know, what is that? I don't know, a couple microseconds, and then it turns off, and then it jumps up, and it goes up to close to 400 volts, because that's going to be double your input voltage, you know, whatever was on the cap. Okay, but it actually goes above that, right? It goes up, has a spike, and then ringing. Well, because that's snubbered, that looks the way it does. It actually looks a lot better. It'd be even worse than that if it didn't have the snubber on there. So you can put more snubber to smooth that off even more, but now you're dissipating more heat in your snubber. So there's this trade-off that you do, okay? You put the snubber there to protect your FET, hopefully to, you know, help EMI a little bit too, but you don't want to totally slow it down because that'd be too dissipative and not very efficient. Okay, then it stays around 400 volts, then it drops down, and then it kind of wiggles around. It almost goes down to 200 volts, almost half the voltage. Now, but then it just kind of wiggles around. So what happens is, as that output is taking current off the transformer, once it's satisfied and it's not taking any more current, then you kind of run out of energy, and so it just kind of lets go. The inductor on the output side lets go, and on the primary side you end up seeing this oscillation between whatever energy is left on the transformer and the capacitance from drain to source. Okay, so then you get this wiggle. So that's kind of normal. It's not a big deal. I have a video on a active clamp flyback converter, and this waveform looks completely different. Anyway, you might want to look at that video and see how nice that works. All right, here's our auto restart. So you see it goes for a few cycles, then it says, oh, fault, and then it waits, well, it says about 2.5 seconds, and then it tries again. Nope, still fault, so it waits and tries again sometime down the road, another 2.5 seconds, keeps on doing that. All right, guys, so here's some waveforms. It shows maximum loading, near maximum loading, okay? And you see there's a pulse missing there because it's near maximum loading. So it didn't need all the pulses, so every once in a while it'll skip a beat. So to the right, moderately heavy. So now it's skipping a couple beats. Now what we have is medium loading on the bottom left, and now it's skipping more. It pulses a few times, skips some beats, okay? And then over on the right, light load, it's going to skip a lot more. The pulses are a little bit wider because it's skipping so much that when it does actually turn on, it wants to charge up the bulk capacitor on the output, and then it does it for a couple pulses and then takes a break. And so sometimes that's an EMI problem. So that's a trade-off. And sometimes you can disable this pulse skipping. But anyway, there's another method of controlling the output voltage during different loads, and it's a way of also trying to keep the efficiency good. All right, guys, so the top waveforms is showing as the power comes up, DC input comes up, it waits until it gets to a certain level, and then it starts pulsing. So the bottom waveform on the top left graph, you see V drain. When the drain starts switching, you can see, oh, okay. And also you can kind of see it ramps up a little bit, the switching. It doesn't, the peak of those switching waveforms aren't all level on the left, so it's kind of soft starts is what it does. So it starts off with a narrow pulse, and then it finally goes to a wide pulse to bring up the cap. Because initially what it'd want to do is look at that output capacitor as a short, and it'd try to charge it up real fast, and that caused an inrush current. It could damage the FET doing that as well. So soft starts. Now on the bottom two graphs, you see the other condition. It turns off, it kind of doesn't reverse. When the input voltage drops to a certain point, it stops switching, but it ramps down, so it does a soft stop. So that keeps you from having too much inductive kickback and other issues. So soft start, soft stop. All right, guys, so here is another schematic, okay? This one looks more like it's more complete. It's got your input filter, your bulk capacitors, your snubber, your transformer, and it has a C5, that capacitor at the top. So that capacitor at the top, what it does is it helps for common mode noise. You don't have to install that, but it's nice to put it on your schematic, and if you need it, you install it. And it just helps couple the primary to secondary, and it can help with common mode noise, okay? So that's the reason for that. Now, another thing about that is the physics, is you want galvanic isolation from primary to secondary, so you want to use a white capacitor up there, okay? Safety capacitor like you did in your EMI filter. And it's also usually physically placed by the transformer or by the optocoupler, somewhere around there. Or right through the capacitor, the transformer, and the optocoupler is your galvanic isolation. So sometimes in the schematic you draw it that way, and that winding on the bottom right corner, the one that's coming backward to the chip, you know, through D6, it's charging a bulk capacitor C6, and then it comes back through. That's your bootstrap winding. And so, again, sometimes people call that an auxiliary. They'll call everything auxiliaries. But that's actually a bootstrap, and it powers up the chip once it's up and running. So it's an efficient way to power the chip, so you're not dropping voltage from your input high voltage down to your low, whatever, 12, 15 volts. You come off with that voltage off your transformer, okay? I usually show all my primary outputs on the left side of the transformer, my outputs on the secondary side to the right side. But I think they're just trying to keep the schematic squished together. So yeah, there you go. There's your optocoupler. You know, now in this case, there is an L on the output. You don't need that because the transformer acts like your L. So, you know, because the transformer in a flyback looks like an inductor. So it charges up your bulk capacitors just like an LC filter does on your forward converters. But in this case, we have a L2 and it says ferrite bead. So that's for high frequency. Thing that's interesting in this schematic is C11 is 100 microfarads. That's kind of big for high frequency. I would think that I'd put maybe C10, C11 on the left side, take a ceramic high frequency cap to work with that high frequency ferrite bead on the output side, like say a 10 mic or even less if you need to. But 12 volts, it's easy to get a 10 mic ceramic to do that, or even a 22 mic, or several of them. But anyway, that I think would do a better job for high frequency filtering. All right, so here's an example layout. Now look how tight this is. Inputs on top left, comes in, there's a chip, you got your ground, and the chip's right on it. The source pins are right there. The drain is right off the primary transformer. So you got the source pins and the drain pin real close to the transformer. So when it's switching, there's a power loop right there, a current loop, and that current coming off your bulk input capacitor is going to come through primary winding, down through your D of that chip and over to S and right back to your filter cap. So it's a really short loop. Then on the output side, you can see the windings, the diode that comes off the winding. You have a single diode, right? And that diode goes right to your bulk capacitor and then right back to the other pin of your transformer. So again, a really small loop. And physically, you can see your white capacitor on the top, your transformer, and your optocoupler. So that gives you your galvanic isolation, gives you safety spacing on your board. So yeah, this is, you know, a nice example of a good layout. Okay, guys, so if flybacks are new to you, I think you're getting a little more familiar, right? I'm going to show you the board again, and now when I show you the board after looking at the data sheet, maybe it'll help kind of see how things are placed and the positioning, and yeah, let's talk about it. So let me just show you that. Okay, so let's just talk about that. Let me show it to you, okay? Okay, guys, again, bulk capacitor feeding the transformer, okay? Okay, so nice close-up view. Here's our transformer. There's the chip. So the ground's going to come off. You know, the source is going to be right next to the ground pin. The drain is going to be tied right to the transformer, and it's going to switch current from that capacitor way over there through this loop. So we want that capacitor like right here, so that loop is like just really short, right? Really small loop. All right, so see this cap right here? That's a Y cap. It kind of looks like the same kind of Y caps that are in the EMI filter, right? This Y cap here is right by the transformer, just where you want it, strapped across the input to output. And your opto isolator is also right there. So here's your transformer, here's your spacing, your safety spacing right through here. So this is your secondary side and your primary side, okay? Now also, you can see how many diodes there are, so you can kind of count how many outputs there are. And you can see, if you look real close, you can see how two of the diodes go these two caps, one to each cap, so there's two outputs. I have a feeling this is a plus and minus setup. So right here we have these guys, and they're all tied together. I even ohmed them just to make sure. And then the other output I'm talking about is this guy. So you can see from diode, there's a trace that runs down to this guy. So there's the outputs. Pretty cool, right? All right, guys, different setting. I'm on vacation. My family, Marcy, Jeff, big thumbs up, took us on a vacation. It was very nice. Music festival. Foo Fighters tomorrow. So a bunch of good music out this weekend. Awesome. I don't know if you can see me very well, but the background looks better. So hey guys, flybacks, they're good for low power stuff, usually under 100 watts. Sometimes you go higher, maybe up to 200 if you're pushing it. They're great for high voltages, like on televisions. They used to do that for the high voltage CRT. And so they're great for high voltage, great for small power stuff. Because the transformer acts like an inductor, you don't need that inductor on the output. And also, you notice there's only one diode. You don't need the flyback diode because it is a flyback. It only conducts during part of the pulse, and you know, where a normal forward converter would use two diodes on the output. So instead of two diodes, you only have one diode and no inductor on the output. Unless you just want high frequency filtering, which I always recommend, but then you can do it with the ferrite beat. So hey, big thumbs up to my patrons, big thumbs up to my members of my channel. I think I've got 4, maybe 5 now. I'm not sure. I think I have 4. I think I had one dropped off. So anyway, I think I'm back to 4. And there's a super thank you button down there. All different ways. Patreon, you join for as little as $1 a month. Or you can just hit a big old thumbs up and like the video and share it and subscribe and hit the notification bell. All that kind of stuff helps the channel too. So thank you guys, appreciate it. And just wanted to get a video out while I'm on vacation. And yeah, I'm a contractor, a defense company, and when I'm gone, I don't get paid. So I took off a day, but hey, family took me on this vacation, so I figured it was worth it. So this is beautiful, right? Okay guys, thanks a lot. Oh, and by the way, Snowmass, Colorado. It's near Aspen, so yeah, kind of a pricey area, so I'm glad I didn't have to pay for this. But all right guys, thanks a lot. Thanks for watching. We'll see you next time.